Hello and welcome to the world of parallel programming. So, in this session, we are going to learn more about recap and theoretical uh, recalling of whatever we have used in the earlier sessions. So, we can know we have appropriately brush up our concept for parallel programming and the directives that we have used so far. So, with that in mind, let's see what we are going to see. So, in so far that we have learned is some of the basic directives for a heap runtime API. So where one of them is a dim3. So if you notice that we use the heap kernel via macro and we also use a heap directive for a triple chevron and we were using a dimension 3 to get our threads and blocks allocated. So which is nothing but X, Y, and Z, what we were getting from our hardware system information. That is the maximum size. But minimum default would always be the one. So you always have a one dimension. That's for sure. So X value 1, Y value 1, and Z value 1. So that means you have the sum records. Now, what we can see is like if you notice and whenever we are writing a kernel function we are using a directive which is called as this kind of like global if you recall, and the other possible options for this is a device. So if we use a device instead of a global, which would look like something as if this. So if we are using this device directive and then we are writing our kernel like say void and hello GPU. So in this kind of case, what would happen that the function is only visible and accessible by the device, which is our GPU. And the global makes the function available for both GPU and CPU. Now, what we can see is like these are all the details. So when we are saying that the first symbol, like if we are using a macro, then it is using this kernel name, grid dimension, block dimension, and the dynamic shared memory sign. These are all the data structures that is internally defined into the heap runtime API. And this is what we have used, like example kernel that we are launching. And if you're looking for more detail, we can always refer to the official documentation of the heap at the Rock'em Docs, and we can get a more information about the same. So this is about the directives. Now, ongoing forward. So another important thing when we are working with the parallel program is like when we are harnessing the maximum power, the another concept come is like how we are defining the variable and what is the size limit and how the memory utilization we can do. So as you can see over here that uint32, so that is nothing but unsigned integer of 32 bits. And so with that, this is called as a precisions. So these are the precisions which are the important to know when we are working with the GPU. And these are various precision point and how that precision points have been implemented and been used. So on forwarding the lecture and any of the use cases that you may come across, so you will always notice into the performance of the system that what is the number of flops we are being achieving or what is the speed up we are achieving in terms of a precision. So let's see why. So let's come with here. So FP64, which is highest level of a precision. That means that it is using total 64 bits in order to represent a value. Now, now if you see the first bit is always a signed bit and another 52 bits is a Manchester bit which will be representing the fraction, and the 11 bits later will be representing the exponent value. Okay, so with that, you can see that the 52 bits will be representing the value and exponent bits is nothing but 10 to the power 11, that many bits. So actually 2 to the power 11, we can say to be precisely when we are working with the bits. So those bits, so 11 bits would be used as an exponent, which is a multiplier. So how many bits is being shifted? So this is how the precision value structure has been calculated with the combinations of a fractional bit plus exponent bits. So if you just want to imagine, you can imagine a simple decimal system where we may write a number value as something called as this. Let's say if we are using a decimal system, we can write some number as say 3 9 5 6 multiply by 10 to the power of 78. Now this 7090, if you see, it's not using the all the bits. What it is using is a few bits. So let's say if you have 1,000, this is also value. So with this kind of structure in mind, what is happening that it is storing the exponent bits and the fractional bits. So with this power, what has been happening that we can store more larger values into the 64-bit representation. So what you can see is this kind of implementation when we come to the C or C++, the data type is named as a double, so which is a double precision. And if we go to the implementation into the Python level, so in the libraries like a TensorFlow, it is defined as a tf.float64, and in the PyTorch, it is defined as a torch.float64, which is eventually redirecting to the torch.double. So it's both the same for a PyTorch. Now, if we go, the another precision comes is a FP32, whereas in UKC, as a sign bit, it is always 1, then 23, it's a Mantis bit, and 8 for exponent bit, and its implementation is a float in the C++ language. And the same, if you can see in the TensorFlow, it's a float32, the PyTorch also, it's a torch.float32. Now, same goes when we go for the FP16, it is 10 fraction bit and the 5 exponent bit. But if you notice, FP16 is not a standard data type which is supported in C, C++. There are certain libraries which enables that, but in the default, the C and C++ does not support the FP16 data types. But if you can see, there have been a libraries in the TensorFlow and PyTorch which implements this precision because the GPU supports it. And for the same, we need to check out our spec for whatever the GPU device you are using to make sure that whether your GPU supports any particular precision or not. Okay, and this is also called as a half precision because it's not FP16, it's FP32, it's FP16. And the same way, there is another data structure which is bfloat16. So this precision value has been supported only on a few systems. So again, not every devices that you have which would be supporting the bfloat16. And the same goes for TF32. So if you see, the difference is coming with the number of mantissa beats and the exponent beats, and based on that, we can have a different number of a range for the numbers that we can get. And on the other hand, we can also know that how it would perform the faster. So if you see that what is the difference between FP16 and bfloat16, as bfloat16, it gives a higher performance. The reason being the simple. So in order to convert the bfloat16 to FP32, it's easier because if you notice, the exponent bits are the same, which is 8 for FP32, 8 for bfloat16. So converting from FP32 to bfloat16 or bfloat16 to FP32, it's much easier compared to the FP16 because the implementation has been a different. So this is a primary reason that you will see this kind of difference, and you need to see that how we can achieve the better performance during our execution. So you can just take an example. Say if you are having a multiplication of a two value, let's say value 1, which is a one variable, and multiplying with the value 2, it's another variable. And let's say if you have defined the both value 1 and value 2 as a bfloat16. So when you are going to multiply bfloat16 with bfloat16. So if you think of that, you are going to occupy the maximum available size from bfloat16 at any one point and another point, then eventually you need a higher precision data structure in order to store the result value, which would be nothing but you need to go to the FP32. And if you are using a bfloat16 for this kind of calculation and storing the result into FP32, it would be much quicker than into the FP16 to FP32. So this is being the primary reason. And not just that, you may have a case where you can have a multiplication where one number may be FP32 and another may be bfloat 16. So this is also the case which we need to take into account for. And according to use case, this kind of a behavior and the precision that we are ended up choosing would matter. And as we are seeing the last data precision, which is the TF32, so only a few frameworks and a few platforms has the implementation. So like for example, in the PyTorch, if we are to use this TensorFlow 32, so Tensor 32 is a precision type. And in order to utilize that, we need to see that we are enabling the backend. So if the backend is enabled, then it would try to use this TF32 performance, which would give even the higher performance. Okay, so with that, like happy programming and hope you enjoyed the session. Then if you enjoyed, then please do like, share, and subscribe and share with your